Just briefly kind of review some of that stuff. Okay. So I'm excited, like this chapter finishes and we dive into controls and things like that. So okay, maybe we'll start it today. We'll touch base. Okay, so stability of discrete time systems was not like, I did not make a comment on it, but I think it's pretty clear from the solution. So does anybody remember what is this solution of a discrete time state space equation? Like if you have xk plus 1, so what is xk? It is a matrix a to the power k x0, right? And then everything else, but it depends on matrix powers, right? So if we are talking about the stability of discrete system, it is dependent on this guy, right? A to the power k. So instead of matrix exponentials, we have matrix powers. So things are multiplied. For example, if A is lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, if I take matrix power of a to the power k, what happens? It becomes lambda 1k, 0, 0, 0, lambda 2k, 0, 0, 0, lambda 3k. So what can you say about the stability? Like we want all the terms of a to go to 0 as k goes larger and larger, right? That's the goal. That's the stable means, or at least not grow, right? So if I'm taking powers of the eigenvalues, what can you say when the system will be stable and not stable based on your previous knowledge of continuous system, right? So magnitude of eigenvalues. Remember guys, so eigenvalues in general can be considered complex with either both real and imaginary parts or just imaginary or just real, but they can still be considered, say, in a general form, complex numbers, right? So alpha plus j beta. So the magnitude of a lambda will be alpha square plus beta square, right? So as if the magnitude is strictly less than 1 for all eigenvalues, then system is asymptotically stable, right? Because 0.1 square, 0.1 cube, 0.14, whatever. If it is less than 1, that number will go to 0. The smaller the number, the faster it converges to 0. Okay? But, and if any eigenvalue is greater than 1, magnitude, then toast it, right? So, yes?
Are our eigenvalues limited between 0 and 1, or can we have negative?
So we are talking about magnitude here.
Oh, no, never mind, that's a dumb question, sorry.
Magnitude is always going to be positive.
Yeah.
Okay, so positive. So now we are just saying whether it is less than 1, equal to 1, or greater than 1. There are three things, right? So if it is equal to 1, then you can see that the powers does not make any difference. It does not change anything. So it is similar to having eigenvalue 0 in the continuous time case, right? So same condition applies. So if you say that if the system is marginally stable as long as all the eigenvalues magnitude is less than 1 or 1 and the Jordan block associated with eigenvalue 1 is just 1 by 1. Otherwise it is unstable. Okay, so that I wanted to cover. I think there is one homework problem there which talks about a discrete time system. And about linearized systems now, right? Last time I think I covered that. So your linearized system delta x dot equals to, after you linearize, right? Find Jacobian at an equilibrium point, you get this system, right? A delta x. So you can still comment about the stability of linearized system around that neighborhood by the eigenvalues of A. Same properties apply. But just be careful if the answer comes to be marginally stable, because there is a problem here that, because this is a first order approximation of your system, you can never be sure that when system comes out to be marginally stable, whether it is actually marginally stable or not. Because There are a couple of examples I gave, like for example, x dot equals to minus x cube, x dot equals to x4. All of them are nonlinear systems, right? I can say for sure that this is asymptotically stable and this is unstable system. But if you linearize it, what will you get? Oh, sorry, x cube. What will you get? You will get minus 2x square. So delta x dot equals to this into delta x. At equilibrium point is 0, right? So the eigenvalues for both of the system is coming 0. Right? What would you say if you apply the stability analysis? You will say that it is marginally stable. Both the systems are marginally stable. But if you perform the nonlinear Lyapunov based analysis, you will find out that one system is asymptotically stable, another is unstable. So basically, when system comes out to be marginally stable for a linearized system, you don't have enough information to comment on the stability. So okay, so that is what I want you should write in. If you are asked about thing and you somehow get a system is linearized system to be marginally stable, then you say, hey, it's coming to be marginally stable, but it is linearized, so we cannot comment. We might have to do more analysis. Okay. So those 2 points that I wanted to cover. I think you have homework problem where you have a nonlinear system that you have to linearize. Sounds good? So the next important thing that I want to discuss today before we move on to controls is any questions on this? Okay, so the new topic that we are discussing, so far we have been discussing internal stability of the system, or it is also called Lyapunov stability. So don't get confused when Lyapunov term comes. It's like stability of x dot equals to ax, okay, or x dot equals to atx, okay, or x dot equals to f of x, whatever, okay, anything. So basically we are just seeing what happens to x when it starts somewhere, whether they go to origin or not go to the origin, whether they are bounded, not bounded, right? That is what we are commenting in the internal stability. So this is internal stability or Lyapunov stability, right? And it's just somebody named Lyapunov might have discovered these things, and from there on. Okay, so now we are going to Bibo stability. Very quick review for that. And as name suggests, it's bounded input, bounded output stability. So, so the question we are asking here is, if you apply a bounded input, something like u equals to a sine omega t, right? It's bounded. It's time varying, but it is bounded. So what can you say about the output of the system, right? So if you apply this u to the system, what happens to y? And internal, because of course there will be x will still be changing and all. You will find out that even if the system is not internally stable, sometimes your system can be Bibo stable. Okay? And if your system is internally stable, don't worry about it. It is definitely going to be Bibo stable. There is no, like, y equals to cx, right? So if, so not an issue there. But the reverse is not true. Like if system is internally unstable, you can still be Bibo stable. Okay, we'll get there. So let's get into some language here. Okay. So let's define. Let's do a definition of Bibo stability first. Okay, so This is a general statement. It applies for both linear time varying systems as well as linear time invariant systems. Okay, the definition of Bibo stability. Okay, so you will always. I don't know if you have already realized, but if system comes out to be LTI, then things become easier. You have closed form solutions, and finding state transition matrix is a pain for time varying systems, right? So let's say it's a system is called to be Bibo stable if there exists a finite constant, and I'll come back to what all these things mean, G, such that for every input U. So this basically means whatever input you choose, it's forced response. So forced response means now you're applying, means you're applying input. Your input is no longer zero. That's why it's called forced response. Y of f. So the output of the system is forced response because you're applying an input now. Satisfies this thing. Okay. So let's say supremum of t belonging to 0 to infinity. And don't confuse by this terminology. Yes, supremum comes because we are giving a general definition. Have you heard of, you guys know maximum? What is a maximum? What is a maximum? It's the upper bound, right? But the problem is in time varying system, when you start changes how the response matters, right? So there are different initial times where you can start, and because of that, you have a different response. So instead of saying maximum, you say that lowest maximum bound. You are getting my point? The lowest, so you have, let's say, 4 curves, okay? And on those 4 curves, so we are still talking about maximum, but the lowest maximum bound. If you find that bound, with everything else will be smaller than that quantity, right? So if it is LTI system, the supremum is maximum, just equal to maximum. Otherwise, it is called lowest maximum bound, So let's say you get your 12-month salary. So no, I don't think that's a good example there, but I'm just thinking a good example of lowest, when they compute our pensions, they say, okay, which one is your lowest maximum salary in previous 5 years, that will be your pension or something like that. And there is one more thing called infimum. but theorem. Uh, and this theorem say that is your continuous time or CLTV, continuous linear time varying system, is uniformly bounded if if and only if, so this is if and only if, for every entry D. So remember our system is what? X dot equals to AT XT, right? Plus BT UT. No, we are no longer just constrained to this, right? We are now saying that we also have a input to the system, and Y equals to CT XT and plus DT UT. So now I'm saying if D is uniformly bounded, so your D entry has to be, so if D is not finite, like it is some infinite term or something, if that is not the case, then you will see that there is no way we can make Y finite. Whatever you give, and if D is not bounded, so D has to be bounded, like 3, 4, 5, 500, 600, 800, 9, whatever. But D cannot be, and most of the time D is zero, so we are always 99.99% D will be zero in actual real systems. Uniformly bounded, D is bounded, and you can say this supremum of for t greater than equals to 0, 0 to t, gij t comma tau d tau is less than infinity. Let me make things clear here. So if this condition is satisfied, uh, then your system is Bibo stable. Okay, let me explain. Do you guys remember what is a transfer function? What so our transfer function was what? It was g hat s equals to your y hat s over u hat s, right? And you will assume this, your transfer function is a good indication of system's Bibo stability because it is giving you input to output ratio, right? So that's transfer function. And if you take a Laplace inverse of this transfer function, what is transfer function? Transfer function is Laplace of the impulse response. So basically, if g of t will be the impulse response, Laplace inverse of g hat s, right? Agreed? So this g of t is nothing but this gt. So we are saying if, and also you if you remember, g has you can have multiple transfer functions, right? If your system has multiple outputs and multiple inputs, this will be a matrix. This will be g11 hat as g12 hat as, right? So on up till, so there will be m inputs, m1 as, and there will be k inputs, right? So g at 1k. So there will be m into k transfer functions if it is a multi-input, multi-output system. Similarly, your impulse response will also have gij. So this also gt, you can call it, right? Gt will also have, will also be a matrix. Okay. So what I'm saying, what this condition is saying, this theorem is saying, if each element of that impulse response, okay, if you integrate it and it comes out to be finite, then your system is Bibo stable. Otherwise, no. Okay. So let me take. So for example, let's say my g of ij is constant for all the time, 1 or 0.5, 0.2. What will happen if I integrate it to infinity? If I do this integration here, infinite. Okay, it won't be bounded. The because the t will come out, right? Anything like 0.2 into dt will be 0.2 into t, right? So anything, if it is not converging to 0, If you integrate it, things are bad. Okay, so your Gij impulse response, so each element has to be basically a decaying function of time. Okay, and okay, so when we go, okay, now you guys should be wondering what Gij should be. So if you remember, uh, for a linear time invariant, so why are we not saying it in always in the transfer function case? Because linear time varying system does not have a transfer function. Only LTIs have transfer functions. So we can always make same definition or same theorem apply in the transfer function domain, but if it is linear time varying system, then you have to apply this. Okay, so if you remember our solution x of t of a general solution will be e to the power, not e to the power, phi t comma tau x of t0 plus t0 to t phi t comma tau b tau u tau d tau, right? That's the general solution. You have to, if you get the state transition matrix, you can find this solution, right? And what is your y of t? You just multiply c to it, right? So y of t is basically c of phi t comma tau x of t0 plus t0 to t c t phi t comma tau b tau u tau d tau. So this is your g of t comma tau. So basically this is your impulse response. This whole multiplication here is your impulse response. Right? So that's your, if you, I don't know if you remember when we derived our impulse thing, we started with, okay, the impulse response of u is g, and then that's where we started. So that's the logic here. So basically, you have to compute this. If you know your state transition matrix, if you know your C, if you know your B, you basically know your G, T, comma, tau, which is can be a matrix, can be a single element. So each element of this G, I, J, you know, has to, when you do that integration, absolute, this integration here, for each element, this says for each element, right? For both I, for all the i's and for all the j's. So the each element, when you do this integration, should be finite. Okay. So instead of doing integration, as if it is not decaying, that cannot be the case. So it always, each element of that matrix has to decay, or this matrix, right? This matrix here. So your g of t comma tau will be ct phi t comma tau b tau. Okay, so you have to compute this, and if check each and individual element, it will be very clear. As soon as you see if it is t or 1 or constant, if it is not a matrix exponential with negative power or decaying function, you're toasted. We'll take an example and make it clear. Okay. Okay. So, and also there is a term here d of ut also, right? So that's already taken care because d is uniform or 0. So this will be finite. So okay. So let's see if we can, and the same thing. What if you find, if you do it for LTI system, this system becomes to be, this thing becomes c e to the power a t t minus tau b tau, right? Or b. Okay. Yes.
I'm sorry. Can you re-explain, so your y part? I'm with you on the x solution,
Mm-hmm.
linear time varying, but when you get to y, you have your
So what is y? Y is written as ct xt plus dt ut, right? So you just plug in xt. Xt is this. So when you plug in, you get
okay, you plugged in x t.
uh,
Gotcha.
Okay, so
And then D though, so we're assuming D is 0, or is that putting a circle around
yeah, so D, I'm saying that dt ut, because we have made assumption that D has to be uniformly bounded, or 0 is also a uniformly bounded case, right? So D will always have to be uniformly bounded for a system to be Bibo stable. So the condition says, if we go back to our condition there, it says that dt has to be uniformly bounded, and this should be satisfied for each element of the impulse response. Okay, for each element of the impulse response, this has to be satisfied. So D is bounded, and each element of the impulse response, or that's this matrix, uh, this matrix is basically decaying. Okay, and this matrix becomes matrix exponential C into this multiplied by B. Uh, okay, so now you can actually relate things. So if it is linear time varying system, there is no other way. You have to find the transition matrix. There is no other way. You find multiply. Good thing happens is, if this is even unstable, right? If you determine that this is internally unstable, that some terms are not decaying, but when you multiply this, some terms can be cancelled out. So this C and B might provide some kind of cancellation. So even if this phi t comma tau is not internally stable, the multiplication can result to a bibostable system. So that's what I wanted to make clear here. Similarly, if all the eigenvalues, and or maybe one eigenvalue is positive, then this e to the power 8 t comma tau is not stable, not converging. But after multiplying C and B, it might happen that that bad term might cancel out, and you might end up in a. But you can also say that if this is stable, all the eigenvalues are negative, then there is, boom, it is internally, it's bibostable as well. So any asymptotically stable system internally is always going to be bibostable. You can see here, right? Because this e to the power a t comma tau is going to 0, no matter if it is asymptotically stable. So it doesn't matter what C or B is, it is going to be bibostable.
Asymptotically stable, does that not include marginally stable?
Not margin. Marginally, again, has a problem. If I integrate it to infinite, it, so yeah. If system is asymptotically stable, both LTV or LTI, it is going to be bibostable. It's clear here, right? This goes to 0, this goes to 0. C and B does not matter. But if but opposite can happen, that if it is, even if it is unstable, there might be some cancellation when you multiply C and B, and it will be clear when we take examples. Okay, so we can also make a statement that if, right, so if it is asymptotically stable, asymptotically means what? All the eigenvalues in the negative, or for linear time varying system, basically you say that phi t comma tau is going to 0, then there is no need of it, that gij term will definitely go to 0. Okay, so let's take some example now that things clear. Let's say x dot equals to 1 0 0 minus 2 x plus 0 1 u, and y equals to 1 1 x. Okay, so it's our x dot equals to ax plus bu, and y equals to cx, and your d is 0. Okay, now can you find whether this system is Bibo stable or not, right? So you can always do that test whether it is internally stable, asymptotically stable, no, right? One eigenvalue is 1, one is minus 2. So too bad, you have to do the calculations now, right? Otherwise, if both the eigenvalues were negative, then you don't need to do any go further. It's Bibo stable, but it is not there, so I have to go further. So that means first I have to find. So objective is to find the C e to the power at into b. That's what I want to find, right? So first I will need 8 e to the power at. E to the power at is simple because it's a diagonal matrix. So e to the power at is et 0 0 e to the power minus 2t. That's good. And when we multiply c to it, it is 1 1 e to the power t 0 0 e to the power minus 2t. And what is that? 0 1. What happens? So 1 1 means you add things, so it becomes et and e to the power minus 2t, and then you have, sorry, et and e to the power minus 2t into 0 1, and the answer is e to the power minus 2t, right? And now if, so gij is, what is g? It is not I, because it's a scale, it's a single input, single output system. So your impulse response basically is just a scalar. So it is g of t is e to the power minus 2t, right? And now what can you say about it? E to the power minus 2t, when you integrate from 0 to infinity, will it be finite? Yes. So if the eigenvalue was 0 or anything, you would have been toasted, like, because if this was 1.5, anything other than 0 would have been in trouble, right? So dt. So it is Bibo stable, although the system was internally not, it was unstable system, but it is still so. And this is also called pole zero cancellation. If you find transfer functions, right? If you let's find a transfer function here. So I think what is happening is transfer function s minus 1 and s plus 2 comes in denominator, right? And when you find the transfer function, this s minus 1 comes upstairs and things cancel out. You remain with 1 over s plus 2, and then boom. So the transfer function also shows you that. Okay, so there is a pole zero cancellation happening. So there was a pole in the right hand side which was cancelled by a 0. So because of that, system remained Bibo stable. Okay, at least theoretically. Bias pole zero cancellations are not always good things. Okay, so it's always good to have an internally stable system, because it might not be showing in the output, but internally things might be damaged if one state is not bounded. Okay, sounds good. So most of the time we will not be using bibostability properties in our controller design or anything. Okay, it's the internal stability which will matter more, because you can just think of a nuclear reactor and one of the state is the temperature of some turbine or something, right? Even though the output, it does not shows in the output, you don't want that state to be unbounded. So internal stability, I will always go for internal stability rather than bibostability, but it's a theoretical uh, concept. Okay. Same thing you can do, like, for example, I don't know if e to the power t square, yesterday in the homework problem, you had a time varying system where your state transition matrix came out to be phi t comma t0 came out to be e t square minus t0 square. Is it bibostable? No, right? When even if you multiply c and b this side, you will find out, because it's a single input, single output. There is not much cancellation happening there. So it is Bibo unstable, right? If it is both internally and Bibo unstable. So you will have to find out. You can try that. Like, for example, I think we had an example of LTV system where you were getting something, right? T, and I don't remember it, but you have to see if each term is vanishing. Anything less than that is not going to make it, because that integration will build up. Okay. Any questions?
Are we going to go through an example of a linear time varying system?
We can go like, let's take an example. Like, I don't have example here, but we can definitely build one, make one from the homework problem or something. Let's see if I have. Uh, so teaching LTV. Let's see if I can give you an example here. Okay. So in one of the example, we came out to be the phi t comma t0 came out to be this 10.5 t square minus t0 square 1, right? So 10 and these two terms came out to be there. So your system was this x dot equals to 0 0 t0 x. We can assume some b now, plus b will be, let's say, 0 1 into u, and we can also assume some c, y equals to, let's say, right now let's just say 1 0 into xt. What can you say about the Bibo stability of the system? So first I need to find out c phi t comma tau, or t comma t, or whatever. Tau can be anything, and b. So you will see that what that term is. Again, same thing, right? Like, so 1 0 means it will only keep, so it will keep the first row. So it will be one thing. So 1 0 into 0 1. Okay. So what is that output answer? So that is 0. Okay. So that came out to, so your g of t comma tau came out to be 0. Okay. That means when you integrate 0 dt, so that is marginally, that is bibostable. Okay. Because the integration of this till infinity is finite. It is less than infinity. So it is but it could have been a problematic thing if anything other than 0 or decaying term would have come. Anything. Anything 0 or decaying term, which means what? It, anything exponential. But so if this was appeared, this appeared, or that appeared, game over. There is no way you can restrict that integration to be a bounded thing. Okay, so that's how you have to first compute the transition matrix in linear time varying system, then multiply it with C and B, both one side and B on the other side, and check each element of that matrix whether it satisfies that integration quality, whether the integration will be bounded or not. And integration can only be bounded if either it is 0 or it's a decaying term. Okay, if it is either 0, then you integrate, doesn't matter, or it's decaying term. As a, even a constant term, if you integrate, it will blow up. Okay, so that's good. We are kind of completed one theoretical portion of the course. Now, when we design controllers, we will know what our objectives are. And so, one objective is always try to keep x to go to 0, right? So, this is called a regulation problem, that can I regulate x to 0? And you will see that, I don't know if you always wonder why always take x to 0, right? Does anybody, that question comes to your mind? Anybody like? in control systems, uh, one of the stability criteria is taking x to 0, right? So you can always change states and always make that your change of variable such that the desired point is the origin of the system. You can always design systems like this. So, for example, yeah, if I want this vehicle to go here, right? This is x. This is x desired, and this is 0 origin, right? So I want my system to go to x desired rather than going to the origin, right? If my system is stable in this definition, that means it will go to the origin, not to the x desired position, right? So you can always define your state variable to z x minus x desired. You see what I'm saying? Like now your states are z. So now going to z going to 0 means what? X going to x desired. So you can always change your variable such that going to the origin means going to the desired point. You get my point? So we can always try, either it is a desired trajectory or anything. You can always make a change of variables such that going to the origin means then those stability definitions we will, when in that sense, when I say my system is stable, that means it will go to the desired point. Is that clear? Like, don't, so this is very general. So say, when I say x is going to 0 means I can take my x to any point I want. I can always do that change of variable and say x minus xd is the state z, and z going to 0 means x going to x desired. And you will see that in the examples, in the quad rotor example and things like that. But because we want to apply the definition of stability, right? And stability definition is always taking states to the origin. Okay, so our design systems will be like this: that whenever we design a system, we show that it is asymptotically stable. That means x is going to x desired position, or x is going to the origin. Questions? Anybody? Before we, so this is it from the stability side or analysis side of our one. We have some more theoretical things coming, but we'll put a hold on them and dive into some actual problems so that you have an idea for your projects, and then we can come back and visit some other theoretical things like controllability, observability, which are necessary to design a control system. Okay? Yes.
I may have missed it, but on the homework questioning, with the part of the law equation, a to the TP plus PA plus T mu P, I guess I'm forgetting where the T mu P comes in.
Also, you're talking about the homework problem. Anybody did that problem? Number 8? Nobody? Nobody even attempted it? Huh? No? Huh? so, so should I wait before you guys try it, or? Because if I try it now, how about you guys try it and I make a video and put it online for the hint? Because if I give it right now, then it's basically like it's a very small hint if I give, and then the solution comes out. You can relate it to the hint is like you can relate it to the eigenvalues of the system. You can choose your Q matrix like identity matrix, kind of a very simple matrix, and then that mu will show up in the eigenvalues, and just okay. So I can make a video and put it on maybe tomorrow night or something, but at least try it. Don't wait for me to give a solution for the problem. Okay. You tried it or you did? So it's related to this, like, so if you remember, uh, there was a theorem where we were saying all of these statements are equivalent, right? System is asymptotically stable, system is exponentially stable, all the eigenvalues are strictly negative, and this A transpose P plus PA equals to minus Q. If that for any Q, if this equation is satisfied, all of these statements are equivalent, basically. So now you go backward and see. So the hint is start by showing that all the eigenvalues of A have real parts less than minus mu if and only if all the eigenvalues of A plus mu I have real parts less than 0, or are eigenvalues Eig of A plus mu I is less. I don't know, like if you can. Do you know how you compute eigenvalues? Si minus A, right? You find the determinant of that. Can you make a can you make a connection to this? It's just Ui instead of Si. It's kind of very similar, the structure. So if these are 0, that means no. I think that quiz is important on Tuesday. Okay. Anyways, give it a try. See, A plus mu I and Si minus A is kind of simple. Only only sign is different. So that's how you compute your eigenvalues. Anyways, let's move on. Uh, any questions on stability as such? So let recap, right? What we have done so far. So a little bit recap. Uh, so we can put system into different forms, right? We have state space. So x dot equals to ax plus bu, and this is a linear state space, right? So y equals to cx plus du, or x dot equals to f of xu, y equals to h of xu. This is linear. This is non-linear. Okay, so state space, you can have transfer function g hat s equals to y hat s over u hat s. If this is known, you can get a transfer function c si minus a inverse b plus d. So you can get transfer function for state space. You can find the solution, right? Solution of a system. Not for this. This is kind of out of reach, but you can always get for LTV or for a linear time invariant system, you can get a solution xt equals to e to the power at x0 0 to t e to the power at minus tau b u tau d tau, right? And then you can also get a linear. The general solution is phi t comma tau or t0 x t0 plus t0 to t phi of t comma tau b tau u tau d tau, right? So this is the general, and from the solution, what we learned? What did we learn from finding out the solution? That you need matrix exponentials for a linear time invariant system, right? And we need matrix state transition matrices for time varying system, right? And if you look at these matrices closely, you will find that for a LTI system, the stability convergence depends on eigenvalues. Here, you will have to actually check what happens. Okay, so that's it. Like, and if the system is discrete time system, it's instead of matrix exponential, you have matrix powers. It still depends on eigenvalues, the magnitude now instead of signs. So that's what we have learned so far, like, right? So not much in the last how many weeks, I don't know. Uh, this is what we have learned. Like, we can see the solutions and now make prediction, actually comments on the stability. And so the best thing you can hope is system is linear time invariant, right? After that, things get crazy. Questions? So now the objective is okay. So what? Question comes in like now. Okay, we know what happens. So next thing will be, see, so there are two things that I want to, let's stop this